Hello and welcome to my channel. My name is Good, and this channel is all about a single player 2D survival game that I'm working on called Struggle to Survive. My game is set in 1820 America during the time of the beaver trades and the Rocky Mountain rendezvous. If that piques your interest, I invite you to subscribe to the channel and follow along on my dev blog. You can find a link to the blog here on my channel. If you find this video interesting or helpful, please consider liking and subscribing. I really do appreciate your interest in my game. As you can see, I'm developing my game in the Godot game engine. As of this video, I'm running Godot 4.1.2. I've had several requests from those that have watched previous videos on this channel to explain the method I'm using for creating my tile maps and creating the game world. I'm doing it a little different than maybe you've seen in other videos. My game world is seamless, and not only seamless, but there's no chunking. Back in the day when I was creating this game in Unity, I ended up developing a chunking engine, and it worked really well. I was very happy with it. Um, and for various reasons, I moved from Unity over to Godot, and maybe one day I'll do a video on the reasons why. Um, and irrespective of the news of late regarding Unity's price increases and things like that. I made my decision a long time before that. But anyway, I found Godot to be just an incredible development platform, and it's perfect for what I need for my 2D survival game. And coming into Godot, I wanted to change it up a little bit from what I had done in Unity, and I decided that I wanted to create a game world of millions of tiles. If I so choose to do that, I want to be able to do that, create a game world of millions of tiles, and I want to be able to have no chunks. I want the game world to be loaded into memory and to not have any chunks so that there's no chunk loading delay as you're moving around in the game world. Now, there's that type of a scenario is challenging, but I enjoy it, and I've come up with a methodology for creating my game world and for moving my character around the tile map that doesn't require chunking. It also is seamless. The game world, when you reach the right edge of the game world, you will keep going east, you'll arrive on the west side of the map. North, you'll arrive at the south side, and etc. And the idea being that I want the player to be able to roam around and not have to face the edge of the game world. And I've been able to do that with this implementation. And today I want to show you three ways that you can create something similar using three different methods for generating your tile map and for generating the game world. So here I have a tile map demo scene that I've created just for this video, where I've taken all the code that I'm using in my game and basically placing it into a single script. I guess I should say that I'm in the process right now of converting my game from Godot 3 to Godot 4. In Godot 3, I chose to use GDScript. And I did that because I wanted to learn GDScript. I want to be able to, there's a ton of sample code out there in Godot, GDScript, and I wanted to be able to read it and understand it and translate it. I am a software engineer by trade. My language is C sharp. And so when I decided to upgrade or migrate from Godot 3 to Godot 4, I also decided that at that time I would go ahead and translate all of my GDScript that I had written so far into C sharp. C sharp is faster, and I enjoy working in C sharp. I do it every day. So that's one of the things that I wanted to do in migrating from 3 to 4 was to translate these scripts. So I've got a single script, and this video is going to be showing you C Sharp. Um, Hopefully that'll be of benefit to you. And if you're not using C Sharp, maybe this will be a motivator to get you to use C Sharp in your project if you are working on a game. Now, hopefully the code will be easy to follow. There are no signals. Everything is just in one single script. And I've placed it here so that I can just kind of run down from the top down to the bottom and show you what I'm doing and how I'm doing my my tile map in my game world. The scene itself is very simple. I have a single node 2D at the top, and below that I have a tile map, and then below that I have a player, which is just a sprite 2D. I'm going to use the old Godot logo here for that. There's a label attached to the sprite 2D so that I can show position on the map as the player is moving around. And then, of course, we've got our camera 2D, which is attached to the player, meaning that the camera is going to be following the player as the player moves around in the game world. Now, the three methods that I'm going to be showing you are going to be a procedural generation of the game world using the standard Godot template, which this looks, I'm sure, very familiar to any of you that have been working with Godot 2D tile maps. So I'm going to show you how I generate the game world using the standard template and using the terrain system in Godot 4. So we're going to do that first. And then after that, I'm going to show you some of the negative uh, points about the terrain system, not the least of which is that it is extremely slow. And so the second way we're going to, or the second way we're going to look at generating the game world is rather than using terrain sets, we're going to be using a sprite atlas, and it looks like this. We're going to be using a sprite atlas, and I'm going to be showing you how I created my own bitmask engine to basically do what terrain does, but many, many, many times faster than the current implementation of terrain. So in other words, these guys are going to be using terrain, but when I switch over to my bitmask solution, I'm not going to be using these. I'm going to be using my own sprite atlas, and then show you how much faster that is than using the terrain system. And then finally, I'm going to show you an alternative to using a sprite atlas for all the various pieces of your tile type. And instead, I'm going to show you how you can use a single tile, single sprite for each tile type to generate your game world. Again, much faster than using terrain. So that's what I have in store for you today. Now, before I get into the code, I want to talk about the sprite atlases, the images that I'm using. And I want to try to explain a little bit about what is needed to create a game world where you don't see all these edges on the tiles. Okay, and some of you may know this already, and if so, that's great. But the idea behind using the sprite sheets to generate the game world is that you want to be able to create a game world where your different tile sets blend together, or at least meet together edge to edge. And in order to accomplish that, there's a real simple way you can do that. And that is simply to make your sprites twice the size of your tile size. Now in my game, the tile size is 64 by 64. So my tile sets, the textures each one of these are 128 by 128. They're double in size. And you will see in a little bit how doubling the size allows you to allow the edges of each of your tiles of various tile types to blend together such that you don't see the transparent edges around each one of your tile types and the sprite atlas. So that little trick of just simply making your sprite size twice the size of your tile size enables everything to blend together. Okay. Now let me show you this tile set here in paint.net. I'll just bring this over. Now you can find the template for this on Godot's forum. It's all over the place. You can find it. And the idea is that I just created basically various colors to represent the tile types just for the purpose of this demo. But what you'd want to be looking for if you're creating or you're going to use the same methodology is you want to find a seamless tile that you like. Um, Make it, if you're going to be using 64 by 64 uh, grid in Godot, then you want a 128 by 128. So you'll see here that my tiles are 128 by 128. Okay, and you want to make sure that if you're creating edges like this, you want to make sure that you basically come up with a template using an edge layout or design pattern that you like. And then it's important, if you're going to be making these twice the size and you're going to be painting them using procedural generation, that the edges all match. Um, that's really helpful. But anyway, I just wanted you to know that if you're looking for a way to get rid of these, the transparent edges, go ahead and make your tile set twice the size of your grid in Godot. Okay. All right. Now, um, these, as I said, the first method we're going to use is setting these up using the terrain system. And so, as you can see here, I have already set up all the terrains for each one of my tile sets. And I have set these terrains up. The terrain sets, I have one terrain set with multiple 4 terrains. And each one of these are, mapped out with all of the bit masking that the terrain system provides. In this video, I'm not going to get into actually setting that up. There's a lot of great videos out there on that. So just understand that the first methodology I'm going to use is going to involve using these tile sets, using these sprite sheets to create my game world. Okay, so let's move on now to this guy, and this is going to be the second methodology that I'm going to use, where I have no terrains. So it's not going to be. You can see here these are all the terrains that I've set up for these first 4 tile sets. Okay. However, these guys do not use terrain at all. I'm simply using the images, the atlas images, to create my own bit masking solution. And in doing that, another difference between using these and using my own custom sprite sheets here is that when I'm using these and I'm using the terrain system, I'm matching on corners and sides. Okay, so the terrain system, and if you're not aware, um, the terrain system accomplishes being able to match all the various um, different sprites by taking this minimal sprite sheet, and for each one of these, when necessary, it will take, and when it does the bit masking, it will flip the image to match the bit mask. And that's how you're able to accomplish, or that's how the terrain system is able to accomplish showing all 256 combinations by only using this one minimal sprite sheet. And it's because as it's calculating, it will flip sides and flip images to be able to accomplish showing the correct sprite from the sprite atlas based on the bit masking. Now, when I decided to spin up my own bit masking, I realized that I didn't need everything. I didn't need all of these because for the purposes of my tile map, I can get away with just using sides. So I can just match on the sides. And I'm going to show you how I did that. And thus, because I only need to match on the sides, I don't need all these sprite images. All I really need is these guys here, all right? And the one that is matching on all corners and sides, which this is the filler for when everything around this tile, everything around the tile is the same tile type. So I use this filler. So I needed these, and I also need the filler. And what I ended up doing was creating, something that's a little different. Um, the left side of the sprite sheet, and then down at the bottom, I added a couple of the center pieces to act as variants. And I'll explain that in a little bit. But again, these are all 128 by 128, okay? And there's one sprite on this atlas that I don't use, and that's the bottom left corner. And the bottom left corner is my original 128 by 128 seamless image that is used to create all the rest. And I'm just keeping it here on the sprite sheet, but it's actually not an atlas image that I'm actually going to use. I'm actually rather going to be using these others. All right, so let me show you what that looks like in paint.net so that you can see nice close-up. And basically, notice these numbers here, 1, 2, and 3. The center tile, that is the one that's going to be painted when everything around it is the same tile type. My bitmask engine is going to choose from this image 1 or 2 or 3. Now, when I show the bitmap being or the tile map being generated, you're going to see 1s, 2s, and 3s, right? And what I do is I just randomly select one of these 3 as my center tile whenever I am searching through and making sure that everything is matching. And I do that to break up the pattern of a seamless tile. Even though tiles are seamless, you can still pick up little patterns with your eye as you're looking at them. And so since I had some real estate here on this image, I thought, let me take my center tile and let me create 3 flavors, 3 different variations, little differences between the 3, such that when you're looking at the game world and you're seeing the tiles, it breaks up the pattern a little bit so that it looks more random. And it turned out actually really well. At the end of the video, I'll show you my implementation of all of this in my game, and you'll see how the variations break up the patterns that you see. All right, the third way that I'm going to show you in this video is how to use a single tile with faded edges to accomplish the same thing that the terrain set and my custom bit masking does, only without having to determine what tile from the atlas to display. So let me show you that in Paint. This is what it looks like. I've just taken my 4 tile types, my stone and my grass and my water and my sand. And these again are 128 by 128, okay? And I've just used an effect in paint.net to fade the sides. See if I can remember where that is. There it is. Fade edge. You can go to paint.net's website and look up the plugin Fade Edge, install that plugin, and then what I ended up finding out was when you're creating this guy is you start out with you start out with your base tile, this guy right here, and you essentially, the fade effect is the setting for this is to set it to 32, because I have a 128 by 128, which means the center of this tile, or excuse me, of this image is 64 by 64. So I fade 32 pixels all the way around, leaving the 64 by 64 unfaded in the middle. And that's how I was able to accomplish that. All right. And so that's what we have. We have these fades, and I'll show you how I use that when we get into the code. All right, it is time to look at some code. Now, as I said at the beginning of the video, I'm developing my game using C Sharp, and I'm in the process of porting it from Godot 3 to 4. So I've got a lot of scripts that are GD script that I'm translating into C Sharp as I go. And so for this video, for this demo, I created a single C Sharp file and put all the code that was needed for generating the tile map and for showing these three methods into this one single file. Now, some of you may be disappointed to know that I'm not going to take this file and host it somewhere and give it to you. And I want to explain why. It really doesn't matter how experienced you might be or inexperienced you might be when it comes to a language like GDScript or C Sharp. The number one way to learn is to do. And so while you're going to, in this video, you're going to see every single line of code in this file, all 403 lines. I'm going to walk through it and I'm going to explain what is in this file. But for you to learn this and to understand this in the best possible way, you should code it yourself. You can pause the video as I'm walking down through the code. If you want to set this up yourself and play with it and learn from it, by all means, do so. That's why I've taken the time to do this. But I'm not gonna just give you the code, because I feel like I'd be giving you or doing you a disservice. To learn it, the best way to learn it is to do it. And so follow down through and open up your editor, whatever you have. Now I'm working in Visual Studio 2022. You might be using Visual Studio Code for your C Sharp development, but I'm using Visual Studio 2022. And for those of you that don't know, you need, excuse me, you need to use Visual Studio 2022 for Godot 4 because of the .NET version that is supported in Godot 4. In Godot 3, you would be using 2019, Visual Studio 2019. This was another reason, by the way, why I wanted to move from Godot 3 to Godot 4, because I don't want to work in 2019 C Sharp, the .NET that is supported in that. I want to be able to use 2022, .NET 6, and all the nice new features of the more modern .NET languages, C Sharp language versions. So this is the file, and let me go kind of walk down through it. This file is gonna be attached to the top node, which is a node 2D. Okay, so we're gonna inherit from node 2D. By the way, you don't need the namespace. In fact, if you create a C# file from Godot, it'll create the file and open up your editor for you, but it will not provide a namespace. I have the namespace here because it's built in, because this file is a part of my game. And so I have a namespace, but you don't need the namespace. You can start it off with just your public partial class, since you're implementing or inheriting from node 2D partial class, and then just start, laying out your properties and methods and things like that. All right. So Tilemap is a reference to the tile map in the scene, and this Sprite 2D is a reference to the player. Label is to the player label. This is an integer tile size. This is the size of my tiles, or excuse me, my tile map in the game world. Okay, the cell size is 64. I've got a walking speed and a running speed. These variables are used to allow me to either walk or go very, very fast so that I can demonstrate the um, um, performance of using these three methods. You'll see that the performance is going to be vastly different. And then, of course, the player speed, which is going to be assigned based on whichever one of these are chosen. Now, this vector 2i is my map size, and I have a couple of static sizes that I'm using for the purpose of testing. So a tiny map, 200 by 200, that's 40,000 tiles, small, medium. I have it set up right now on medium, so we're going to be generating 360,000 tiles in the game world when we run this. And I've got a large, and extra large goes all the way up to 1,000,000 tiles, and you can go even larger if you have the memory. If your system has the memory. Now the view size is the viewport size, and I have a couple of different sizes here, depending on what resolution I want to run the game in. So for 1080p, 1920 by 1080, I'm using this huge view, and it's basically a view of 37 by 25 tiles, which is 925 tile view. Now, let me pause right here and explain the general concept that I'm using, because this concept, you may have seen it in other places. I think I've only seen one other person do something similar to this. Otherwise, I don't know of any other person that's using this type of methodology. But this kind of harkens back to 2017 or so, when I was first working on the concept of a 2D survival game. And back then, I actually was doing it in as a website. And my thought was to make it multiplayer and all of that. And so so I basically was using um, web technologies to create my game. So what that meant was that I was using JavaScript. And so I got used to the idea back then of every time the player moves, I refresh the screen to show the player at the player's new position in the game world. And so when I say that I'm loading up all of the map into memory, I'm loading up a dictionary containing all the tile types in their respective locations, their vector 2s, okay, their XY coordinates. But when I'm actually showing the game world on the screen, I'm only showing what you can see on the screen. I'm only generating those images themselves. And so these sizes correspond to the number of images, or excuse me, the number of tiles that I need to display on the screen to fill up the screen based on the resolution, but also to give a border around the screen of images, because some of my, like in my Flora engine, some of my flora, some of my trees are 4 um, tiles high. And so I want to be able to show the screen and also show the trees that are slightly off screen, but I don't want them popping. You know, I don't want the user or the player to be able to see those trees popping onto the edges. And so I expand the view, okay, which is the viewport. I expand the viewport, and I offset the tile map so that I can show the center where the player is, and at the same time provide enough tiles that are out of view to be able to spawn in those trees and to have it look like you're just walking through the forest and you're not seeing the edge of anything. So that's the goal. And I hope that you'll see this as we go along and as I show the code and as we talk about this. Um, so the idea is that when the player moves along a grid pattern, okay? So WAS and D, diagonal movement is also supported. But the idea is that when you move the player's going to go from the tile the player is on to a new tile, which is based on the movement, and the player automatically walks or runs to that location and then stops. The moment the player stops at the new tile position, the entire view is wiped clean and redrawn. Now, I know what you're thinking. You're probably thinking, wow, isn't that going to take a lot of time to get, to completely erase 925 tiles and redraw them, or 713 or 513? Actually, no. It in two of these implementations, I can tell you that the paint, the redrawing, the removal and redrawing of the tiles on the tile map is is in the milliseconds, way down in the milliseconds. You might even be shocked to see how fast the tile map can be drawn using two of these three. The first method is rather slow, but the second method, where I'm doing my custom bitmask engine, and the third method, where we're only using the the faded edged single sprite per tile type, blazingly fast. Okay, you will be impressed, I think. All right. So that's basically what it is. So it's just a repeat. We generate the game world, then we put the player somewhere in the game world, and then we generate our view. And when we generate the view, we paint these tiles. And then when the player moves, since the camera is attached to the camera follows the player. When the player reaches his destination, which is the next tile in whatever direction he's going, the entire view is wiped clean. All the objects are refreshed, and you're at the new position, and it's blazingly fast. Two of these three methods are blazingly fast, I'll say. Okay, so in order to accomplish this, we're going to create a tilemap dictionary. The tilemap dictionary is going to be, the key to the dictionary is a vector2i, which is the xy coordinate of the image on the tilemap. Okay, and this integer array is some data that I'm storing about each one of the tiles, and we'll cover that in just a minute. I do create a world noise dictionary, which is basically once I generate the noise, I save it in a dictionary, because who knows, I may want to use the noise itself as a data source for a map, a little mini map or something like that. So I can do that. And then Atlas Dictionary Sides is my bitmask dictionary that I'm using for the purpose of the second method for this. So my selected world tile is, a lot of these variables are self-explanatory. This is my view rect. This is the center of the view, the map size in pixels, diff and direction and target and player map position. These are just all variables required to make the engine work. There's a busy Boolean and a game running Boolean. Those are kind of pulled in from my implementation of the game. Not necessary. You could probably get away with just one. Okay, so in my ready function, I'm going to get the node for the tile map and the player label. I'm going to set my map size, my view size. My direction is going to be, this has to do with the movement of the character. So we're going to start him out at vector2, 0, which means he's not moving. Target is a vector2, 0, which means there's no target. The view center is basically the center of the viewport. Player position starts at the center of the viewport. Player speed is set for this demo right now. I've got it set to the running speed. And the player map position is the starting tile, um, which what I've done here is I've set my start tile to be 100, 100. So my XY coordinate starting tile is 100, 100. That's going to be my starting tile. And then I initiate a new dictionary for the world noise and the tile map, create new dictionaries, and then I populate my Atlas dictionary sides. I'll show you that in just a little bit. I get the view rec and I set my map size being view size times view size. There's a difference variable, which you'll see in a little bit. There's a map offset, which you'll see in a little bit. You'll hopefully understand what all of this is once we get down. I'm sure you will. I'll do my best to describe everything for you. And we set the tile world position. Now, the tile world is the tile map. So we're going to set the tile map position to the map offset. And we only do that one time. We never move the tile map once we initially set up in our ready function. Um, there's randomizing Godot's random generator. And importantly, we are generating our new world first. And then after we generate the new world, we're going to generate the player view. The world is going to generate all the world data. The view is going to get called every time the player moves. And you'll notice, so I've got this method here, player moved. Every time the player moves, we set the player's position back to the center. That's going to put the sprite for the player right back in the center of the screen. And then we're going to generate our player view, which is going to wipe the screen and repaint everything. Is moving is just basically a check to say, hey, is the player moving? Is the direction of vector 2, 0 or not? If direction is not vector 2, 0, then that means the player is still moving. Set player position is basically just setting this variable player map position is going to be based on whatever position we pass in. And then we're calling the player moved to indicate that we've made a move. The player has moved. Get player is just the getter for player map position. We're returning that position. This is important. This is the get player input. Now you always, what I found in 2D physics process movement for player movement, you always want to create a method for your movement itself and then call that method in physics process. Because if you don't, if you just use the input, grab the input from the keyboard and use you override that input method, then what happens is it slows down your input such that you will have to press your keys more than one time. You won't get a continual movement, nice smooth flow. So the way to fix that is to just call the get player input in the physics process. And by it constantly calling this every physics frame, what you end up getting is you can hold down the keys and you can change direction by just simply changing directions with the keys. And you don't have any delay other than just the frame and the processing of the movement. So I hope that makes sense. So every physics frame, we're going to be calling this method. However, if the player's moving or the player's busy, we're going to return. We're not going to do anything. So we're just going to call it, check for movement. If it's not, or if they're still moving, we're going to do nothing. Otherwise, when the player reaches his destination, we're going to grab a new direction based on the player input. So direction X is going to equal, and I'm casting this as an integer value because we're not using the float values for movement. We're just using, we are moving one tile at a time. And since the tile vectors are vector 2i integer, then all we need are integer values. So we do an input is action pressed UI left. That's just mapped to my left arrow key, my A. So and if you're not familiar with C#, I'll read this for you as I would a C# developer, so you can kind of get an idea of what all the the symbols look like and what they mean. So direction X equals input is action pressed, then, question mark is, think the word then -1. And when you see a colon, it's an else. So this is an if then else statement, basically. So if action is press UI left, then -1, else if action is press UI right, then a 1, else a 0. There's a one-liner for getting direction X, and direction Y is exactly the same way. Now, after getting the direction, if direction is vector2 0, which means the player hasn't pressed any of these keys, and you can see how if the input is action pressed, we're doing something with it. Otherwise, it's a 0. So we're setting direction X to 0, direction Y to 0 if the player's not pressing anything. Then we're going to return a vector 2. And if that's if vector 2 0, if direction is vector 2 0, there's nothing to do. So we return. So we're gone. We're done. Physics process is done. It's checked. Now the physics process is just going to keep checking, keep checking, keep checking until direction is not a vector 2 0, meaning we have somewhere to go. So if we have somewhere to go, we're going to set our target. And the target is going to be direction X equals 1, then position X, the player's position X plus the tile size. So we are moving in a direction based on player direction. Else direction X equals a -1, then minus tile size. Else player position X. Same thing. All right. And then if we do have a target, we're going to set player busy to true. Now that's going to make it to where this doesn't get called and processed again until the player reaches their destination. Okay. Physics process is pretty simple. We're going to get the input. If the target is not equal to a vector 2 0, that means, hey, the player's moving. We've got to do something, right? So if the player's position equals the target, that means we've arrived at our destination. We're going to update the map player tile. We're going to set the new position of the player. We're going to reset direction and reset target to vector 2 0. And we're going to set player busy to false. So this is a really cool feature of C#. You can actually set multiple variables with the same value by chaining them. Direction equals target equals vector 2 0. All right. Otherwise, if player position is not equal to the target, then that means we're still moving. So we need to actually move toward our target. And so else we're going to set player position equals player position move toward the target, and we're using delta, the physics process, the delta process, or the delta value, the amount of time between frames times the player's speed. And this just allows for smooth movement towards. And this is just going to keep happening until the player reaches the target. All right. Now, update map player tile. So whenever we reach our target, we've got to basically put the player on a new tile map in the world. Remember, we started at 100 and 100, X and Y. So depending on which direction we go, we've got to update that. And that's what this does. Now, this code handles not only setting the player's position to the new tile, but it also handles adjusting the tile the player arrives on based on our game world wrapping around to the other side. So if direction X equals 1, then new tile. So what we do is we grab the current player's tile, and now we're gonna adjust that tile. If direction X is 1, then new tile X plus equals 1. That means new tile X equals new tile X plus 1. Plus equals is the shortcut. Else, if direction X is -1, then it's X minus 1. If new tile X, the value that we just set here, equals map size, that means that we are all the way over on the right-hand side of the game world. If we are all the way over at the right side and we have moved, then we're gonna set the tile position to be the far left side. And this is what enables the wrapping that takes place, okay? Else if new tile X is less than 0, so let's say we've gone west and we've reached the first X position, which is 0, and now the new tile has been set minus equals 1, the new tile x is a negative 1, then we're going to set it to the 1. We're going to set the tile set so that we're wrapping and going all the way back over to the new the left side. And this repeats for the right side and for the north and for the south. So this just allows for wrapping of the game world. Okay. Then we set our player position to whatever the new tile position is. And then once we do that, we set that player label, which will appear below our Godot sprite, our player, to be the new tile position, whatever the position is. Now this is called this is string interpolation, where we are embedding in brackets, or curly braces rather, the name of the variable, which gets translated into a string using this string interpolation. Okay, all right. So moving right along, how do we generate our game world? All right, so I set a watch here, which is a stopwatch in C#, and I set a salt value for the random noise generator, and I'm just doing that so that we can show the same map each time using the 3 different methods so you can see them. And actually, to be quite honest, because of the uh, using the bit masking and because of the way I'm using the single tiles, some of this salt applies and some of it doesn't. But anyway, the map size, I set a local variable here. Map size is map size X. Now, here's how we generate our fast noise light, the new implementation of the noise engine, Perlin noise engine for Godot 4. And I've been playing around with different noise types. You can do the same to see what you like the best. But in this demo, we're going to do noise type Perlin. I'm not changing any of the parameters, just basically using the default parameters. And I'm setting my seed to be, for the noise, to be the salt value that I've set up here. I can comment this out and set my seed to a random. You can do that if you want to play around with the different ones. Now, this part here is important for the random or for the noise generator. I'm not using the noise values. I'm using the noise values from the image that's generated. Because see, in order to have a seamless world, I need to use a seamless noise. And to have seamless noise, I need to get a seamless image of the noise that is generated. And this is the real easy way to do that. I'm going to create an image in memory. I'm going to use my noise and say, I'm going to call this method get seamless image. I'm going to pass in my map size, my width, my height, whether to invert or not, whether to use 3D space or not, which I'm not. The skirt, skirt allows for the seamless aspect of the image. It kind of blends in the seams a little bit, and I have found that 0.2f, a float value of 0.2, works really well for that. They have default is 0.1, but I think 0.2 works better. And then whether or not to normalize. Normalize will basically take all of the uh, pixel values and convert them to 0 to 1 in a range from 0 to 1 instead of maybe negative to positive 1 or something like that. And then I save that image in my root directory so that I can then call that image later if I ever want to use it for anything. I just save it there so I can have it. All right, then I just kick to the console. I'm generating a new world. Here's the loop. Map size for X, map size for Y. We're going to set up a variable for pixel, and we're going to get the pixel from the image, not the noise, but the image. We're going to get pixel X and Y. Now, this get pixel is going to have an image, or excuse me, a pixel color value. And actually, the pixel color value, RGB, those color values, they're all going to be the same value when you do this get seamless image. Okay, so the image value is going to be exactly the same. So I just picked the first one. You could pick 0, 1, or 2. I picked the first one since all 3 color values are the same in the image. Okay, so we're grabbing the color value, and that color value becomes basically the value that's used for determining the tile type. So we've got our tile key, which is a vector 2i, x, and y. So we're grabbing the key position in the tile map, and we are setting the next thing we do is we set the map noise dictionary record to be the tile key. This is vector 2i key. So we're going to take the tile key, and we're going to take the pixel value, the float pixel value from our image. And that's our map noise dictionary. Now, remember I said that we store some tile data in the tile map dictionary? So this is that data right here, okay? And this is just an integer array that I use. You can put any kind of information you want in this, as little or as much as you want. Just keep in mind, the more data you're storing, the more memory you're using, okay? In my implementation, I only need a few pieces of data. I need the first integer value in my data is the tile definition, and I use the pixel value to determine, and I'll show you that in a second. The second is an atlas um, x and y coordinate. Now, I only use these for my second implementation, which is my custom bit masking. So basically what I do is when I generate the game world, I set the atlas image x and y coordinate at the very beginning to 0. I'm just setting them to 0. And in doing that, since I don't know what my atlas image is going to be until I actually determine that using my bitmask engine, I just set the flag on this record, this XY coordinate vector 2 to dirty 1. So it's dirty. Okay? So that's what I do when I prep for my custom bitmask engine. Now, if I were to implement the terrain system, and that's the way I was going to go, I wouldn't need these three because they're not even referenced. Okay. If I'm using the third method, which is using the faded images, I don't need this either because I'm not picking an atlas image to use. I'm hard coding it to just a single atlas image. So these three are only used to use my bit masking. So set tile definition. This one is real simple. All I'm doing here is I've determined that 0 is going to represent stone, 1 is grass, 2 is water, 3 is sand, and I'm basically on a scale of 0 to 1.0, setting the value, returning the zone. This is the type. The zone is the tile type that I'm going to be using, and that's all. That's all I'm doing with that. Okay. Once we're done generating the game world, after we set the tile definition, then we actually write the tile map dictionary record, the key, and which is the XY position, and the tile data, which is this integer array that I'm setting. That's it. Stop the watch, get some millisecond elapsed time so I can print out the map size, how big it was, and how fast it was generated. Okay, and then I set the game running to true. All right, here comes the fun stuff. So every time the player reaches the player's destination, there's going to be a generate player view that gets called. And you saw that up here where where we're basically generating the player view when the player reaches the position that they have arrived at. We're generating the player view, okay? So the way this works is we've got to create some arrays. These are only used in the terrain implementation, and you'll see that when we get down further down, okay? The terrain implementation requires that we store the terrain, all of the terrain locations for a single terrain type into an array. All right, so we're going to use the Godot collections array of vector 2i. So these are going to store the 4. Use terrain. These are basically my switches where I am turning on and turning off which one we're going to see when we run the code. So right now I've got it set to use terrain. I want to show you that one first. Then I'll set use terrain to false, and I'll use the custom bit masking. I'll set it to true, and it'll demo the custom bit mask. And single tile will use the faded edged tiles, a single image I'll set that to true, and we'll get a chance to, by turning these on and off and switching them, to see actually how fast this player view gets generated. All right, so we start the watch variable for some how many updated tiles get called when we're using the second method, the custom bit mask. First thing we do when we generate our player view, we're going to clear the tile world. This here really isn't necessary for the demo. Uh, actually, basically when I'm creating trees, I create objects as children of the node that this script is attached to. And when I refresh the player view, I wipe those clear. And that's what this is doing. Um, since I'm not using trees in this demo, since I'm not creating the trees, those nodes actually don't exist. But here's how you would do it if you had trees and you wanted to refresh and move, everything in the view has to be refreshed. So if you have trees or buildings or anything like that, any objects from the scene tree would need to be cleared. Well, you don't want to get rid of your player node. You don't want to get rid of the tile map. You don't want to clear that, because if you look here, you'll see that the tile world and the player are children of the tile of this node 2D. So as trees are added, they get added as children of this tile map. Okay, down here somewhere, and it just kind of builds this list. So when you clear the tile map, you don't want to delete this, you don't want to delete the player, and anything else you don't want to delete, you'd want to make sure you exclude them in the script. Okay, all right. So then we get our player position, because the new position the player is in is where we're going to start from, and this basically sets up the starting position of the view, the upper left corner of the view. And then we loop through the view size here. We get a tile key variable. We set our map position to be starting X plus the current position we're in. And what this does is this adjusts for the location in the game world. So if we're at position 100, 100, it's going to get the starting position, and it's going to add to it the X value so that you're painting starting at 100, 100 instead of painting at 0, 0 on the tile map, or excuse me, in the tile map dictionary. And this matches what we had in the player position, setting of the player position. It's a little bit different. You're getting the absolute value because we're working with vectors, float vectors here. But anyway, you uh, setting this up allows you to do the map wrap, this code right here. Okay. All right. Now here's where we're getting into the three different methods. If I'm using terrain, for each one of the positions in the tile map that I'm painting the view for, what I'm doing is I'm getting that tile record. The first integer is the position. Okay, so I'm saying, hey, I'm I'm going to switch the value, which is the position, tile type. So tile record 0 is the tile type, and view position is the vector 2i. So I misspoke. Tile record 0 is not the position. Tile record 0 is the tile type. View position is the current XY coordinate in the grid. Okay, and all I'm doing is I'm adding to these arrays, the whatever. So if tile record 0, if it's type stone, I'm going to add it to the stone array. If it's grass, the grass array, etc., all the way down. All right, and that's all I'm doing with the X and Y positions and the terrain types, is I'm building this array so that I can use the terrain to interpret this. Otherwise, if I'm using my custom bit mask, I am getting the dirty flag, because I'm going to do something with that dirty flag. If the tile record is dirty, if dirty flag, if the fourth value, which is 0, 1, 2, 3, the fourth value is 1, it means that I have not yet processed that tile in the tile map. Therefore, I need to figure out what tile image from the atlas to use. Because I'm not using terrain, I'm going to create my own mask, and I'm going to use that mask to determine what I'm doing. So we have this update tile record sides, this method here, and I pass it in the key. So if the record's dirty, we're going to clean it up. We're going to choose what the side is, what the atlas image is that we need to use. So I'm going to control click to jump to this method. Update tile record sides. Now what does that take? It takes in a vector 2i, which is the XY coordinate. And then basically what it does is it sets a target and it checks, it's going to create a result value from position that the player is moving towards. So if the target X equals key, then target Y equals key, and we've got our if key Y equals 0, then map size Y minus 1, else key Y minus 1, and target X equals key X. Now that describes the values you're going to get when you go north, okay? X doesn't change when you move north. Think about the tile map and the XY positioning, okay? X moves horizontally and Y moves vertically. X starts at 0 on the left and Y starts at 0 from the top. And so basically what we're doing is we're saying, hey, if we are we take the current value that we have, the current position, the current tile, that's our target, and we are determining based on the player, if what we're trying to do is we're trying to say, okay, my tile is this tile, 100, 100, XY 100, 100. So we're going to say, okay, what is north of that tile? And this is only recording, we're only looking at the sides. So we're only checking north, east, south, and west. So what is north of this tile? So in order to get the north, we calculate a target. The target here is north. Then we check our tile map dictionary. We pass in the target's coordinate, and we check to see if that target coordinate, if the tile type, which is 0, matches our key of 0. So is this the same? If it is, then we're going to add 2 to our results. Now, so if it's north, we add 2. If it's east, we add 16. If it's south, we add 64. If it's west, we add 8. Say, Eisgood, where did you get those numbers from? Well, you remember we have this thing called Populate Atlas Dictionary Sides. So here's what I did. I created a dictionary of the values that would get created based the results that would get created from checking north, east, south, and west to see if the tiles north, east, south, and west of the current tile is the same kind of tile. And here's how it looks. So I basically, let me jump into Paint real quick and I'll show you exactly what I'm talking about. So if you think about tic-tac-toe board, okay? Now, the center tile is my target, okay? And what I'm saying when I'm checking north, south, east, and west, so I'm not checking the corners, I'm only checking the sides, okay? I'm basically saying, hey, if these have values, then it's going to create a unique bit mask calculation, let me say. All right. And the way we do this is we establish some values for each of these squares in this tic-tac-toe board. All right. So what we do is we say, okay, well, if the player, if we were using the corner here, let me do this. Let me jump to text so it's a lot easier. All right. So here, that value is 1. That value is 2. That value is 4. That value is 8. You know from the terrain system that the center tile, a center bit mask is always set, so you don't have to add that. Next is 16. This is 32. This is 64. Oops. Sorry. 32. This is 64, and this is 128. The combination of any of these together creates a unique identifying value that represents the combination. And that's the part that's important because that's how bit masking works. You know, if if 1 and 16 are both, if the east image is the same as this one and the northwest image is the same as this one, then that's a unique combination value total of 17. You won't get 17 in any other combination. Okay? That's the way this works. Now, since we're only checking to our north, east, south, and west, then what I do is I can take my image here. Okay, I can take this image and I can look at the edges and I can say, okay, well, 1 would be this upper left corner. It's not the same, and 2 is not the same, and 4 and 8 and 16 and 32. The center 64, that one matches, and 128, that one doesn't. So for this image right here, which is Atlas 00, the value that I would get for this would be what? Would be 64. So if we go back to our code and we look, we see in our dictionary sides, this dictionary that we're going to be using to grab the correct Atlas image, if the value coming out of this method here, if this result, okay, Atlas Dictionary Sides result. I'm getting a key from this dictionary. These are the keys. The key is the total that's generated from comparing the sides. Okay? And that's why this is demonstrated here visually. 2, 8, 16, and 64. Vector 2, 0, 0, the Atlas 0, 0 image would be a value of 64. And you would do the same for each one. And you don't have to calculate them because I've already done it for you. This is the calculation. Now, because I'm using a custom atlas, all right, remember this atlas, this bit masking that I'm doing here, this only works with my custom bit mask. That's what this is. I'm replacing the terrain system. So the center variations, this is where I'm tapping into 90, which is 64, 16, 8, and 2. That's 90. So the variation that we're going to use, we're actually not going to use 1, 4. We're actually going to use 1, 4, 2, 4, or 3, 4, depending on which image gets randomly selected. Okay, and that's what the purpose of this is. If the result is 90, I have one of those filler tiles. Okay, then the atlas coordinate that I'm going to use is a random center tile of new coordinate, a random of 1 between 1 and 4, which is 1 to 3. And that's what we're going to set the coordinate to, the y coordinate. The x coordinate is the same in my image, okay, in my sprite sheet. Okay? All right, and so that's basically it. That right there is a bit masking solution that you can use to automatically pick the correct image for your tile map when you're trying to match the sides. And this only works for sides. I did create one for corners, and I did create one for sides and corners, which uses the whole 256 image set of images. But that's for another day. Okay, so we get back up here to our player view. So if we're using terrain, we're going to be creating an array. If we're using the custom bit mask, we're going to check for a dirty. And if the tile is dirty, we're going to call that update tile record. We're going to set the tile record using the key, and then we're going to implement a counter on our updated tile so you can see how many got updated. Okay. Otherwise, if the tile record is not dirty, that means we don't have to go through this process of checking. So it's already been recorded. So the dictionary already contains the proper tile record 1 and tile record 2 locations. Remember, when we generate the game world, we set 1 and 2 to 0 because the atlas image is 0, 0. And I could have picked any one. Just basically it's dirty. That means this is useless. It's not accurate. We've got to clean it up. But once we clean it up, we set these values to whatever they properly should be based on the tile map and the dictionary. And then once we do that, then we can just call set cell, tile world set cell. We can pass in the layer And you'll need to make sure in your tile map that you set up a layer for each one of your uh, tile sets. Then we give it the view position, which is the XY coordinate. Then we give it the excuse me. Then we give it the source ID, the layer, which is in my case 0, the vector2 coordinates, which is the view position, the source ID, which is the ID of the sprite sheet. Okay, in this case for stone it's 4, and then we cast a new vector or create a new vector to I for the position. That's the atlas coordinate of the image that we're showing, and then whether or not to use the alternative tile. All right, and then so we do that for stone, grass, water, and sand, and that's it. That's all we have to do. Now, if we're using the single tile method, we already know which one to use for, we're going to use the tile set tile ID number 8, and we already know that stone is atlas coordinate 0, 0, grass is 0, 1, blue, water is 1, 0, and the sand is 1, 1. So we don't have to go find them. We don't have to guess. We don't have to do anything with bit masking because we already know the position of the atlas images are these 4 positions. And so in the case of using a single tile, we're just setting it based on the tile that are the image from the atlas, and that's it. That's all we're doing. Now, if we're using terrain, we've got to do one more thing before we stop the view, creating the view, and that is we actually have to call the set cell terrain connect method to actually process all those positions in the arrays, those 4 arrays that we assigned, and that's what we're doing here. We're basically just saying, okay, layer 0 in our terrain system. We're using the stone array, which that's all the stone tiles. And this is the terrain set that we're using. And this is the actual terrain that we're using, which is 0, 1, 2, and 3. And you can see that in the settings of the terrain. Okay. Once we do that, we stop the watch, the elapsed time. We grab our view count or tile count, and then we just print something to the console to let us know what happened. Okay. Now, for the sake of you being able to write out this code before I actually show what these are doing, I'm just going to kind of scroll down through here. You can stop it wherever you want. Stop the video and write your code. This is how you, especially if you're new to C# or you're new to Godot, or you might even be an experienced developer. Um, if you are, you know what I'm saying is true, that there's nothing like physically typing this yourself. It is invaluable to getting it into your brain, how things work and why the code reads the way it reads. So you just kind of walk down through here and I'm just going to keep scrolling nice and slow so that you can copy this code. And as you enter this code in, you're going to get great joy from being able to run it and tweak and play around with it. And maybe you'll find one or more of these methods. I'm actually using I'm using 2 methods. I'm not using terrain bit masking. Okay, it's woefully slow, and you're going to see that. Okay, but I am using a combination in my game of my own bit masking and single image, the faded image. Um, I'm using a combination, and it works well for me. Okay, there you go. That's all the code. Now here's what we're going to do. This is where it gets fun. This is where we actually get to see the fruit of our labor, right? So we're going to come down here, come down here to our player view, use terrain. I'm going to start with that one, okay? And I'm going to show you how that looks. So I'm going to run this scene. This is using terrain, the terrain system in Godot. All right, so here's what we've got. Now, you'll see here a 600 by 600 world of 360,000 tiles. were generated in 1,965 milliseconds. Okay, it's 1.9 seconds. That's pretty fast, right? Okay, the view was drawn. Dirty tiles only applies to my bit masking, so that doesn't apply here. In 254 milliseconds. So 713 tiles were created in the view on the tile map in 254 milliseconds. Okay, now 254 milliseconds, that's about a fourth of a second. And when I move, you can see that the camera moves with the player, and as soon as the player reaches his destination, boom, the whole view, the whole tile map is cleared and redrawn. That that's pretty good, really, right? I mean, this is redrawing the map. It looks like you're moving and everything is still the same, that nothing has been redrawn or repainted or cleared. You're not even seeing the clearing, right? No jump whatsoever. Okay. And you're seeing that we're getting speed of, refresh is, around 250 or so milliseconds. All right. So that is this method of using the terrain system. Now I want to show you for purposes of comparison. Okay. I'm going to hold down the A and I'm going to move west, and I'm just going to hold the key down. Okay. And I want you to watch what happens. See that? So it's a little jumpy because we've got a quarter of a second delay between. Now I'm going to go right. We've got a quarter of a second delay there. I'm going to go southeast, go west, go east. Okay. Now, moving a single position looks natural for using terrain. Holding down the key and running, not so much. That looks very choppy, doesn't it? Okay. I'm going to stop this now. We're going to go in our code, and I'm now going to change it to the custom bit mask. Now remember how fast? It was about a quarter of a second, 250 milliseconds, right? For the terrain system. This is why I say terrain is slow. Now, terrain might be fast for another implementation of the Tilemap system, but for mine, where I want to wipe and redraw so that I don't have chunks, so I have a seamless, chunkless game world, drawing on dictionary data, it doesn't work for me. And you're now going to see why. So now we're going to use the custom bit mask, which is my own custom bit masking solution. I'm going to run this. All right. So generating our world. Remember I said that when we have my eye is deceiving me. Remember when we had these, that we have the 1, the 2, and the 3? These are the variations of the center tiles. Okay, so now you can see that it's randomly assigning the center tiles, not the edge tiles, but the centers, the ones that match north, south, east, and west. Then we're doing a random, right? I will show you in my implementation where you'll see that in effect in just a minute. But we're here to look at numbers, right? We're here to see how fast this bit masking engine is. So check this out. Oh, let me go to my output window. Probably help, huh? All right, so check this out. The world's generated in about the same amount of time because the same engine generates the game world. But check this out. The view was redrawn with 713 dirty tiles. When you first launch the game, jump into the game world, all the tiles are dirty, right? You've not touched any of them, so they all have to be cleaned up. So they end up getting cleaned up. And we're able to clean them up in 37 milliseconds. Now, what does that mean? That means that my custom bitmask solution is actually painting the tiles and choosing which tile needs to be shown in 37 milliseconds, as opposed to the terrain system doing the exact same thing in 250 milliseconds. But it gets better because now that these tiles are dirty, the only tiles that we are going to refresh or to clean up, so to speak, are going to be the ones that haven't already been cleaned. Now, every tile you see here has been cleaned. That means when I move west, I'm going to pick up the left edge in the dictionary that hasn't been cleaned yet, and thus it's going to clean up those 23 tiles to the west. Okay, and I actually wasn't fast enough with my finger to lift off the key because I actually moved twice. But here's what I want you to see, because when we cleaned up the left edge, we did not have to clean up any of these other tiles. So the refresh included a cleanup of 23, a rendering of the 713, but look at the time. Look at the speed. 5 milliseconds. Now I'm going to do what I did with the terrain system. I'm going to hold down A and I'm going to go west. And I want to show you what this looks like. You ready? Look at that. Will you look at that? We're getting 5 and 6 millisecond refresh and cleaning up of 23 dirty tiles. Now, I went west that time. I'm going to go east. And by going east, it means that the eastern edge some of these have already been cleaned, right? So when I go east, no dirty tiles to clean. And now my speed has increased. I'm now between 4 and 5 milliseconds cleanup. And it varies based on the load, processor load, and things like that, okay? So if we go diagonal, we're going to get 50 some dirty tiles that will need to be eventually, see, 53 dirty tiles that are clean. But you'll notice, look at the speed. 53 tiles, we're down to 2 milliseconds. Okay? In other words, the engine, the Godot game engine, is optimizing itself as I run these tiles. And it's creating an absolute amazing thing to me because we are painting every move. I can't even move a single spot. I'm going so slow. I mean, so fast. Every move is wiping the view, redrawing it, cleaning up dirty tiles as necessary. Now that is what I can do with my tile bit masking engine that you just saw. So let's look at the third one. So we're doing good. We're doing anywhere from 1 millisecond to 5. Maybe I saw 6 somewhere. I'm not sure, but anyway, that's what we're doing with that one. So let's change it up again. This time we're going to use the single tile method, which basically is one image per tile type. How fast is that? Oh, it's fast. It's very fast. And at this point, whether or not to use the custom bit masking solution or to use the single tile really falls on your own personal preference. I think the single tile looks great. You may not. You may look at it and go, wow, eyes good, that's ugly. Well, okay. But consider it. I mean, it's just a single image, okay? But because we have made it 128 by 128, you get a blending effect. You'll see. All right, so we're going to use the single. Let's come back here, have it compile the .NET binary, and let's see what we got. Oh, eyes good. That looks so blurry. Well, I know, but that it's meant to be blurry. The purpose of it is to be blurry, because I mean, how many times have you had to Google, or maybe you haven't, but I know I have many times had to Google, okay, how do you blend one tile type to another tile type? How does that work? How do you do it? And you know what? There are countless videos on, okay, here's the best, greatest, latest, greatest technique for blending. Well, I accomplish blending with the 4 images, and because they all blend the same, they all blend into each other because they're twice the size. They're 128 by 128, so they're blending. Okay? Now, let's take a look at the numbers. Let's go to our output window. Now, here's what I want you to notice with the blend. No dirty tiles, right? Because we don't have dirty tiles. Okay? We're getting a 4 millisecond rendering, okay? But now watch this, because I think what you're going to start seeing, you're going to start seeing some threes somewhere, if I remember right from my testing before I did this video. And I'm about to make myself a liar. Okay, oh, there it is. See the threes? The threes are gained because you're only really showing the one. You're not pulling in multiples. But still, notice this, will you? That we have a game world generated from a tile map system, drawing from a dictionary of positions with a single image for each tile type. And it works. It works well, and it's fast. Now, I I will say that I'm very happy that my bitmask engine is pretty much just as fast as this. It isn't just as fast when I start adding in a bunch of other stuff. This is where I think the single image solution is best realized performance-wise when you have a bunch of objects in the game world and you don't have to try to run the bit masking to figure out which image to from the atlas to show. That's where you gain a little bit. But you know what? 3, 4, 5 milliseconds. I'm happy with that. That's phenomenal in my mind. Okay. Now I'm going to stop this, and I'm now going to switch to my implementation, not not the Tilemap demo, but I'm actually going to run my game, and then take a look at it. And so, in order to do that, what I want to do is I want to take a look at my world generator, and I want to come down here to my okay. So I've got this show flora true and false. I'm going to turn flora off for a second, and I'm going to set this to use tile sets. Now, let me just say, the Tilemap demo, in the Tilemap demo, I've got use terrain, okay? In my implementation, I don't use terrain. And the reason I don't use terrain is because of that 250 millisecond delay. It would kill my game to have to wait a quarter of a second to refresh. All right. I'm already consuming more time generating my trees, um, and I'm not even happy really with that. I've got to optimize that some more, but I don't even use this. So you're not going to see use terrain in mine because it would be woefully slow. You think generating those tiles is slow, 250 milliseconds, generating all those trees. I'll put it to you this way. Seems to me like I recall when I was testing it way back before I even created my terrain bit masking solution to replace terrain. I want to say it took like 800 and some milliseconds to generate the scene with my trees, which is almost a second. That's not tenable at all. Okay, so just letting you know, you're not going to see that because I'm either using the tile sets or I'm not using the tile sets. So I'm either using my tile sets, or and in that case I'm checking dirty flag, or if I'm not using the tile set, I'm using the single image. Okay, so let's jump into this and see what this looks like. And at first thing I'll do is I'll not show the flora, and then the next I'll show the flora. Okay, all right, let's play. All right. Here we go. All right, so what do we got? What do we got? 600 by 600 world of 360,000 tiles containing 107,000 flora objects. Now, those objects are created in their own flora dictionary, and just like with the tiles, I'm not rendering 107,000 Flora objects. I'm actually only rendering the ones that show up in the scene, okay? Tile count 713, flora count in this scene here is 181, okay? Everything was generated in 63 milliseconds. Now here's what I want you to see. And I've got my character instead of now here's what I want you to see. And I'm just kind of doing some random directions here. So you can see that it's doing the same thing. It's generating the 23 or the 37 or the 50 some based on how many clean tiles. See, so now we're in the 53, so we're running both edges when we're doing our update. But this is what I want you to notice. I'm getting 30 to 40 to 50 to maybe 60 sometimes milliseconds. Okay? That's less than a hundredth of a second. And my tiles are getting cleaned. My flora is getting generated. All of my flora objects are getting generated. And it's doing it in 30, 40, 50 or so milliseconds. Now, those of you that watched my video on Godot 3 and using the same identical technique, only I didn't have to create my own custom bit masking. That's because the Tilemap system in Godot 3 is miles faster. I mean, it is so much faster than Godot 4. So there's a lot of work yet to be done in the Godot 4 game engine, especially with respect to the terrain system. Okay, and in terrain system has a lot of great new features in it in Godot 4. But as far as raw power, I do that terrain determination in Godot 3 using the same setup basically that I have now that the terrain system is set up for in Godot 4, and I'm getting numbers that are better than this. I'm getting 20 and 30 milliseconds. Okay. There's two reasons for it. Number one, the terrain system is just woefully slow for my implementation. But the second thing is something I want to mention here. There is no currently in this version of Godot 4, there's no physics interpolation. And that's what's causing this player jittering. Okay. You see this little bit of jitter? I'm going to go full screen. Just see that jitter? That little jump? That's because there is no interpolation being applied. Okay? Sometimes the jump is worse than others, but if they would implement the interpolation for physics, it smooths that out so that you don't have that jump. Now, this is how fast the player would be running in my game. Okay? Um, let me stop this, and so you can see the numbers. We're in the 30s, 40s, 50s, sometimes 60s, right? So now what I want to do is I want to go into my code, and I'm gonna set my tile set. So using the tile set, I am going to set that to true. I'm going to leave that on. Did I just find a bug? I believe I did. Full disclosure, I'm recording and I found a bug. I gotta figure out why my show flora was set to false and yet it was still showing the flora. Okay, very interesting. I I made a change to that yesterday, I think. So I think I introduced a bug. So I apologize for that. Anyway, I was going to show you the flora anyway. I'm going to use the tile sets, set my tile sets to true. But what I want to do is I want to go into my player engine and I'm going to set my running speed to 2048. Just some ridiculous number so that it can go real fast so I can show you. Okay. And then in my player movement, uh, just checking something here. Okay. All right. All right. So let's give this a try. I'm going to be running pretty fast. Just so you can see the bit masking under a load. of, really, really fast running, and see if what the numbers look like. Remember, we had numbers of 30, 40, 50 millisecond. Get our output there. Sorry about all this jumping around. Okay. All right. So here we are. Now we're going to run. I'm going to stop. Now look at that. Cleaning up 23 tiles, right? Because I've headed west. I've got the left edge to clean up. Over here, I'm not cleaning up any, and then I'm going to pick up the ones from the far right, and and I'm running and I'm running, and I'm generating, you know, all kinds of flora. Look at that, 230, 40, 50 some flora, and of course generating the flora objects is going to make the time a little fast or a little slower, right? But you can see, like, when I hit water, I'm actually using a shader for my water instead of tiles. So it's going to be, it's going to clean up pretty fast. But essentially, what I'm trying to show you here is, and remember I said that I was going to use a combination of the fade and the bit masking. So all of my forest here is bit masked. My grass is bit masked. But my shore, I use the fade because it seemed it seemed to me like fade would be a good choice for the beach, and so it fades, and you can see, if you can tell real closely, the water, because we have a fade effect here. We've got the water running over the shore, but essentially this is what the system does, and I wanted to mention to you also before I close this video. This is the grass. And you notice how it's really hard to detect a pattern in the grass. And the reason is because I have those three variation center tiles that are randomly generated. So you're not seeing the numbers, the 1, the 2, and the 3. What you are seeing are the results of the randomization of that. It breaks up the seamless image so that your eye doesn't really catch a lot of the repeat of the image itself. All right. Well, I hope you have enjoyed this video. If you have, please give me a thumbs up. I sure would appreciate it. And if you want to follow along as I'm working on my game, then subscribe. Also, check out my blog. You go to my video channel, you can see a link to my blog. And I thank you for your time, and I hope you've learned something today. Until next time, thank you.